Hi everyone, in this video I'm going to go through the beginning of our last unit, which is about sequences and summations. This often leads to something called series, but that's a topic for Calc BC more or less. So the idea is this is an intro into what is sort of a chain of command in math operations known as sequences and summations and factorials that all have sort of new operations for you to use. So I'm going to show you how to identify a series of sequences between arithmetic and geometric, as well as develop formulas between the two and show you what factorial notation is. So a sequence has a general direction in which they go. They have iterations. And there's two major types. There's arithmetic. That's actually how you say that word, arithmetic. Sort of like the beginning of algebra. And this is often described as addition sequences or subtraction sequences. So for example, if I just said the numbers 10, 12, 14, 16, 18, right, we can see this as an arithmetic sequence because from one sequence to the next, I'm just adding 2. Often we can describe this as basically some sort of linear equation similar to mx plus b, where we have a starting value and some increasing multiplication value. And then we have what's known as geometric series, which is actually a multiplicative identity and property. So we could think of it like 10, 100, 1,000, 10,000. You can see that in each iteration I'm multiplying by 10. And so often what this looks like is some sort of starting value times some value over and over again. And so we actually kind of have general models that are similar to linear and exponential. Okay, we don't want to describe them as linear or exponential. We want to think of them as based on linear and exponential. So this is actually the most common, most famous probably sequence that you'll ever see. 1, 2, 3. And so, you know, if we just get rid of the first one, you might see 1, 2, 3, and you might think, wow, that's 1, 2, 3, 4, 5, and that's it. But because that first one is there, it actually has a really unique pattern. And so you might look at this at first and say, there's no relationship. I can't add 1. I can't multiply by 2 or multiply by 1. Nothing's happening here. But this is a different type of sequence where if I add the two previous numbers, so 1 plus 1 is 2. Now the next two numbers is 1 plus 2, and that's 3. And so we get another type of sequence that is based on the sequence itself. So the next number would be 5. This is what's known as the Fibonacci sequence. So if you go to the notes, I have a link embedded in this photo that takes you to kind of an explanation as to what is that sequence and how does it get used and why do we even care about it, because it seems kind of arbitrary, but believe it or not, has a lot of really interesting uses nowadays and shows up naturally in patterns. So it's a really amazing sequence just to kind of see. But this is a sequence that's not arithmetic or geometric because it's not based on a constant addition, nor is it based on a constant multiplication. So there are sequences that do not fall into either arithmetic or geometric. This is what's known as a recursive sequence because it's based on previous iterations. Okay, so this is just the first couple of iterations. So just to understand how we read this, a sub 1 is the first term of the sequence. A sub 2 is the second term of the sequence. A sub 3 is the third term of the sequence, and so on and so forth. So this really means the first term, and then third term, fourth term, fifth term, sixth term. So if I want to go all the way up to 10, remember that this is the Fibonacci sequence, in which I just add the previous two terms. So a sub 7 would be 5 plus 8, so that's 13. A sub 8 would be 7 plus a sub 7 plus a sub 6, so it would be 8 plus 13, and so that's 21. And a sub 9 would be a sub 7 plus a sub 8, so that's 13 plus 21, and that would be 34. And then a sub 10 would be a sub 9 plus a sub 8, the previous two sequences, so that would be 34 plus 21, and that would be 55. So in these sort of recursive sequences, it's kind of hard to actually find a specific value because you need to calculate every value up to and including the value you're trying to find. And there's other ones, linear models or exponential models, work really well, and we can use them. So here's an example. These are sequences that are based on exponential or linear of some sort. And so you see the end directly. That just basically tells me to plug whatever a value is next to there is the n value. So for this one, I would just plug in 1 for n, I would get 7. I would plug 2 in for n, I get 9. 3 in for n, I get 11. And 13, if you really think about it, the initial value is 5, and each subsequent term is just adding 2. That's really just what this linear equation is asking us to do. If you think about it like that, it's just like, oh yeah, this is so much at 2x plus 5, I'm just plugging in a number for x. And this next recursive sequence is not recursive. It's 3 over 5 to the n again. It just has a value for n, so we just plug in that exponent power. So 3 over 5 is 3 over 5. 3 over 5 squared is 3 over 25. 3 over 5 cubed is 3 over 125. And 3 over 5 to the fourth is 625. So that's it. Now this -1 to the n is actually what we call an alternator. And so what that means is based on whether n is positive, even or positive odd, the sign just alternates. So think about it this way. -1 to the first power is -1, but -1 squared is +1. So all it actually does is just change the sign. So this is what we call an alternating series. So again, I can just like plug in n directly. So I get -1 over 2 to the first. So that's 2 plus 1. So that's -1/3. A squared. So that's an alternator. So that's +1. But 2 squared is 4 plus 1 is 5. A cubed, again, alternates to negative, but 2 to the third is 8 plus 1 is 9. And if I do to the fourth, I get an alternate back to positive and then 1 over 17. So, this pattern is a little bit less distinguishable. It's kind of hard to tell what I'm actually doing. I'm not constantly multiplying by a specific value, like 2 or 3, but there is a pattern, right, that I generated from this. But the alternating n is actually a really common thing. Now with these, sometimes we have a different start. So sometimes I don't exactly want to work with whatever n is, and we have that recursive sequence happening. So this is how we know when we have a recursive sequence. You see how it has a sub n and a sub n minus 1 in both of these? That's when we call recursion, because what that means is that the sequence will just auto-generate the next iteration for itself. So recursive means it relies on the previous value in order to generate it. So we have a starting value, a sub 1 equals 3, so that's good. So let's look at a sub 2. A sub n, so a sub 2 would be 2 times a sub n minus 1, so take away 1, so a sub 1 plus 1. Well, we know what a sub 1 is, that's 3, because that was given to us. And so I get 7. But when I go to a sub 3, I get 2. Now again, I have to go back one iteration. Well, now 2 is actually 7. So I get 2 times 7 plus 1. That's 15. And then 4, right, you kind of see the pattern here. I just take the previous number. All right, so again, that recursive sequence is just me saying, instead of using a value for n, I'm using whichever specific iteration of n is asking me to do. Same thing here. I want to start off with a sub 1 is 3, but a sub 2 is actually 2 to the previous value. So this would be 2 to the third, that's 8. And a sub 3 is 2 to the 8th. And 2 to the 8th, let's see here. 2 to the fourth is 16, so it's 256. And so a sub fourth would just be 2 to the 256. I'm not going to try to calculate that offhand, but you can see how it's really exponentiating very quickly as using the previous power, the previous iteration as the power factor. All right, so if I want to try to build a recursive formula, let's look at these 3 examples. The first one here, first off, do you see the plus, minus, plus, minus? That means we have an alternator. Now we want to make sure that we're using the right term here. So if I use n, that means the first term will be negative. So that's not going to be good. So I could actually do n minus 1 or n plus 1 just to account for the fact that I want the first term, a sub 1, to be positive. So I want that n to end up being an even number when I plug in that value. That exponent, to be an even number. And you see I'm alternating between powers of 3. 3, 3 squared, 3 cubed, 3 to the 4th, so that would just be 3 to the n. So this would be a recursive, this would be a sequence to generate all those values. Now my next one, you should just be able to see it's a plus 3, so we can literally just think of it like this. 3 to the n. Now, you have to be very careful. So this is a sub 1. If I plug in 1 for n, I'm already at 3. So I'm not actually starting with 4. I got to start at 1. Because when I plug in 1, I have to account for the fact that 3 is already going to be applied. So yeah, it's a little bit of a tough one there. Now here's where these things get a little bit interesting. So this is in nature a recursive sequence. And I'll tell you it because we actually just did it in the last example. It's a sub n is equal to 2a sub n minus 1 plus 1. And that's that a sub 1 equals 0, and you go on from there. What's more interesting, if you actually look at the values here, 1 or 0 to 1 to 3, if I add 1 to all these numbers, I get 1, 2, 4, 8, 16. You may be thinking, why is that important? Well, these are all powers of 2. So I could actually write the sequence as 2 to the n minus 1. So this recursive sequence could also be written as a form of an arithmetic sequence or a geometric sequence in which I'm multiplying by a power of 2 every time. Now, unfortunately, it's not actually a true geometric because it's a minus 1 at the end. But do you see how actually some of these formulas can have multiple variants, because how you define a recursion depends on your initial values. So it's possible to have 2 different or more than 2 different options for some. Now factorials. So factorials is not a sequence necessarily, but it is a thing that involves a chain of numbers. So a factorial is a mathematical operation that multiplies every number together, including the number and all the integers below it. So 2 factorial is 2 times 2, so 2 factorial is 2. 4 factorial is 4 times 3 times 2 times 1, so I just multiply everything up to 4 from 1. And so that gets me 24. If I multiply 6 factorial, that's 6 times 5 times 4 times 3 times 2 times 1. I'm pretty sure that's 720. You may want to double check me, okay? So the general form is n factorial. N times the previous number, n minus 1, times the previous number, n minus 2, yada, 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 until you get all the way down to 1. So there's ways that we can manipulate the factorials in order to evaluate things. And this will help us out with some probability questions later on. So here's an example. So if I want to find 5 factorial, this would be 5 times 4 times 3 times 2 times 1. So if I just multiply those, I get 120. Now 3 factorial divided by 5 factorial. So let's see what's going to happen here. Let's write it out. 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. And so, you could do the calculation, but also let's take advantage of the fact that we can cancel things. And we really end up with 1 over 5 times 4. And that gets me 1 over 20. And so one thing you might want to notice is when I divide with factorials, a lot of canceling is going to happen. And this is really common. And you actually want to use this. So do you notice how the denominator is just whatever's left over, right? Between 3 and 5, 4 and 5. So we can use that. Let's look at our next one. 10 factorial over 7 factorial times 2 factorial. So first off, think about it this way. 10 factorial is 10, 9, 8, 7, 6, yada, 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 all the way down to 1. And 7 factorial is 7, 6, 5, 4, all the way down to 1. So you can actually cancel the 7 factorial and get rid of all the numbers between 7 through 1 in the 10 factorial, which leaves us with just 10 times 9 times 8 up top over 2 factorial, which is 2 times 1. So you see how I turned a really long problem just by using some canceling, a little bit ahead of time thinking there, just to reduce the number of terms I'm working with. So I can reduce the 2 and the 8 as well. And so I just end up with this, 10 times 9 times 4, which is 360. Doesn't really make it a really quick problem necessarily, but it doesn't really make the problem longer than it needs to. Now there is a factorial button in your calculator. You'll see a little exclamation point. I'm pretty sure you have to hit second. And you would just do in your calculator 10 and then the little exclamation point, hit enter, and it'll give you the value of 10 factorial. These calculators can only go so far, so you'd be surprised how quickly your calculator actually cannot properly calculate a factorial. Now our last example, n factorial over n minus 1 factorial. Well, again, this is impossible to solve the way it's written. You know, we can't calculate what n factorial is, but we do know that n factorial is n times all the numbers below it, n minus 1 and n minus 2 and n minus 3 and blah, 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 down to 3, 2, 1. So here's how we want to think about it. N factorial is n times n minus 1 factorial. Now take a second to think about that. N factorial is, or n minus 1 factorial is n minus 1 times n minus 2 times yada, 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 down to 3, 2, 1. N is just n. Remember, n factorial is n times n minus 1 and all the numbers beyond it. So we use this as a mechanic to break up the factorial with the sole intention to cancel, because the denominator is also n minus 1 factorial. And if you're not sure why this works, think back to the second question here. What if I did 5 factorial over 4 factorial? That's the same as me saying 5 times 4 factorial. Because remember, 4 factorial is 4 times 3 times 2 times 1, and 5 factorial is the same thing but with an extra 5. So we account for it here. The 4's cancel and you're just left with that. So this is a really common thing to see. And of course we can do sequences with this. So if I do 20 over 2 factorial, that's 20 over 2, and that's 10. Whoopsie. I'm going to use some arrows here. So 20 over 3 factorial. Well, 3 factorial is 6, so 20 over 6, and that would be 10 over 3. Sorry, I don't have my stylus with me, so that's why it's a little bit clunky here. 20 over 4 factorial, well, that would be 20 over 24, and that would reduce to 5 over 6. And finally, 20 over 5 factorial. From our last slide, we saw that was 1 over 20, and so that's 1/6. So we went from 10 to 10/3 to 5/6 to 1/6 very quickly. And in our next iteration, if we did this, it would be probably 1/40th, somewhere in that ballpark. Okay, and then the last major thing I wanted to show you in this lesson is what is summation notation. So it's like factorial, except it's for addition, and they give us a starting and stopping value. So the way that we read it is this value right here is my start. So I start at 1. This right here is my end. Again, I end at k. K could be any number at once. It could be 6. It could be 4. It could be 3. It could be 7, right? So the idea is that I would just add all of those iterations. So I just substitute 1 for I, plus move on to the next number, plus move on to the next number, just substituting in whatever number for I is next until I run out of numbers. So here's an example, 3i minus 2. The summation of it from I equals 3 to 6. So I first plug in 3, so 3 times 3 minus 2. That's where the 7 comes from. Then I move to the next number, so 3, then 4. Now we always do this in whole numbers unless somehow specified otherwise. Truth be told, I think I've only seen that maybe once in my life where that's not a whole number written, or we redefine the function so that it's accounted for. So it's always whole numbers. You don't have to worry about it being fractions or decimals. So 3 times 4 is 12, minus 2 is 10, and then if I plug in 5, that's 15 minus 2 is 13, and if I plug in 6, I get 18 minus 2 is 16. So this summation is equal to the sum of all of these numbers, which I believe is about 46. So that's how we would use it, but that's how I calculate all the individual components. Okay, so let's find a way to express these. So again, I'm just plugging in 2, so 2 times 2 is 4. I've done 2, now I move on to 3. 2 times 3 is 6. Then I do 4, 2 times 4 is 8. Then 5, then 6. Okay, I'll let you add those numbers together, but that's it. And the next one, 2, so 2 squared is 4, plus 3 is 7. Then 3, 2 to the third is 8, plus 3 is 11. And then 2 to the fourth is 16 plus 3 is 19. Again, I'll let you add that. But I hope it makes sense where these numbers are coming from. I'm just basically plugging in a value for I. Actually, that should be k because it's k in the equation. Now q factorial, well, so it'd be 0 factorial plus 1 factorial plus 2 factorial plus 3 factorial. The good news is these are pretty quick numbers. So 1 factorial is 1, 2 factorial is 2, 3 factorial is 6. And I forgot to mention this nice little thing. 0 factorial is actually 1. Kind of misleading, but that's actually the way that works. So don't question it. It's just the way it is. And now this is an interesting example as well. So do you notice how there's no p-value here? It's just 3. So I'm not changing any values. I'm literally adding this value. So that's p equals 0. That would be if p equals 1. This would be if p equals 2. So 0, p equals 1, p equals 2. If p equaled 3, if p equaled 4, and if p equaled 5. So just because there's no variable doesn't mean we can't actually apply the summation. It's just if p was to equal 0, 1, 2, 3, 4, 5, what would be the value? It would be 3 every single time. So we add it every single time. So let's look at a way to write some of these summations. So this is where the sequence part comes handy. So if I look at these are powers of 1/2. So if I want to say 1 over 2 to the I, my first power is just 2, so I want 2 to the first. My last fraction is 16, and that's the 4th power of 2. So that's one way I could write it. My next sequence, a little bit tougher to see, but 4, 9, 16, 25, 36, these are all really special numbers. They're all perfect squares. So let's say n squared, but n has to start at 2 because 2 squared is 4, and has to end at 6 because 6 squared is 36. Now finally with this one, it has no stopping value. When you see dots like this means it's an infinite sequence for the time being. So we're going to write it. Now it ends in n, which means I'm not going to use n in my summation. But if we notice, it's all just multiples of 2. So let's say maybe 2k, where k starts at 1 and ends at n, because I end on 2 times n. And one last thing, to make evaluating much more complicated summations a little bit easier. So these are the general rules. If you have a constant, you don't have to worry about the constant. That can come out front. If I'm adding 2, then I can actually just do them individually if I want. And if I'm subtracting, I can do them individually if I want. Sometimes it's easier to separate them, sometimes it's not. It's a matter of personal preference. This one is a little bit more useful than the other two. Necessarily, it's just a matter of what makes more sense to you. So you don't have to use these, but they're just options. So here's an example, 3b squared. So since the 3 is a constant, I can pull it out. It just lets me not worry so much about the properties or about the values. I can focus on the summation. So again, it would be all the squares from 1 to 2 squared to 3 squared to 4 squared. And so I would add those values up together. That looks like it would be 30. 30 times 3 is 90. Now with this one, again, if I choose to, I actually don't think I would do it for this one. I think I would just do it normally, but just to show you the effect of what it's talking about. Just want to b squared of 4. Okay, so if I just sum b together, 1, 2, 3, 4, and then I sum their squares, 1 plus 2 squared plus 3 squared plus 4 squared. Again, that's all that's really asking me to do. So again, this is 30, 6, and then another 10. Wow, 40. Or you could just kind of do it directly, how I prefer to do it, where I plug in 1, so 1 minus 1, plus 2 minus 4, plus 3 minus 9, plus 4 minus 16. Again, I'm just plugging in 1 for b, and then 2 for b and b squared, and then 3 for b and b squared, and then 4 for b and b squared. All right, so this is 0, this is -2, this is -6, this is -12, and then with -20. So that's all the notes for summation, sequences, and factorial. So we're going to keep using them, but this is just sort of an introduction to how those work. So thanks. I hope that was helpful. See you in the next one.